Welcome to the Cabinet of Science and Fiction. Today we're doing a deep dive into something that honestly sounds like pure fantasy, but it's right at the heart of modern physics. We're talking about the vacuum,
Right.
but not the empty void you might picture, like, outer space being just nothing.
Exactly. It's anything but empty. It's this incredibly active, really strange place. And maybe, just maybe, the source of, well, everything.
Everything from nothing. That sounds paradoxical. So where does this idea come from, this not-so-empty vacuum?
It really stems from quantum theory, and specifically Heisenberg's uncertainty principle. That's kind of the key.
Okay, the uncertainty principle. I remember that means you can't know certain things perfectly at the same time, like position and speed.
Precisely. But it's not just position and momentum. It also applies to energy and time.
Ah, right, energy and time.
Yeah. So think of it like this. The universe can sort of borrow energy, but only for incredibly tiny moments.
Yeah.
Like blink and you miss it short.
Borrow energy from the vacuum itself.
Exactly. From the vacuum. Now, you remember Einstein's EMCR?
Sure. Energy equals mass times the speed of light squared, the famous one.
Right. So if you borrow a little bit of energy, thanks to that equation, you can actually, for a fleeting moment, create mass, create particles.
Wow. Okay, so particles are just popping into existence out of nowhere.
Well, not quite nowhere. They pop out of the vacuum's energy field. We call them virtual particles because they don't stick around. They appear, exist for maybe 10 to the minus 23 seconds, unbelievably fast, and then poof, they vanish, returning the energy they borrowed.
So empty space is actually fizzing, like a quantum foam.
That's a great way to put it. A quantum foam, constantly bubbling with these virtual particles. It's a far cry from the old idea of just static emptiness.
It makes you wonder, though, didn't people used to believe in something called the ether, this invisible stuff that filled space? Was there a worry this vacuum idea was just bringing back the ether?
That's a really sharp question. And yes, initially some people did draw that parallel. The ether was thought of as this absolute background, something everything moved relative to.
Which Einstein showed wasn't needed with relativity.
Exactly. Special relativity got rid of the need for a fixed absolute frame like the ether. But the quantum vacuum is different. Crucially, it has to obey relativity. Its properties have to look the same to everyone, no matter how they're moving.
Okay, so it's not a fixed background. It's more like an inherent property of space-time itself that just happens to be very active.
That's a much better way to think about it. It respects relativity.
Yeah.
It's dynamic, yes, but it's consistent with Einstein's theories, not contradicting them like the old ether did.
And it's not just these fleeting virtual particles, is it? I read that the vacuum can have a sort of permanent baseline energy level, a non-zero energy.
It can indeed. And that's where things get really interesting for cosmology, for the universe on the grandest scale.
How so? What does a constant vacuum energy do?
Well, if the vacuum has this constant energy density everywhere, special relativity tells us something quite strange must also be true. It must also exert a negative pressure.
Negative pressure, like suction.
Sort of, yeah. Kind of tension pulling inwards. And the maths works out that this negative pressure exactly cancels out the energy density in a specific relativistic way.
Okay. Why is that cancellation important?
It leads to something amazing. Think about regular gas expanding. Its energy density goes down because the energy spreads out over a bigger volume. Right?
Yeah, it makes sense.
But the vacuum, because of that weird negative pressure relationship, its energy density doesn't decrease as space expands. It stays constant. It's like the energy is being created along with the new space.
Whoa, okay, that's hard to picture. Constant energy density even as the universe gets bigger.
Mind-bending, isn't it? It's like an inexhaustible energy source tied to space itself.
So this constant energy and its negative pressure. What does general relativity say about that? Because gravity cares about energy and pressure, doesn't it?
It absolutely does.
Yeah.
General relativity shows that it's not just mass creating gravity, but energy and pressure too. And it turns out that a positive energy density like the vacuum's, combined with a strong negative pressure, leads to, well, repulsive gravity, antigravity, essentially.
Repulsive gravity. So the vacuum pushes things apart.
On cosmological scales, yes. And this idea is the bedrock of the theory of cosmic inflation.
Ah, inflation. The idea that the universe went through this absolutely insane growth spurt right at the beginning.
Precisely. The theory goes that in the very first fraction of a second, the universe was dominated by a very high-energy vacuum state. This unstable vacuum had a huge negative pressure, creating this powerful, repulsive gravitational force.
And that drove the expansion.
It drove space itself to expand exponentially fast, doubling in size, then doubling again over and over in unimaginably short times. Then this high-energy vacuum decayed, its energy converting into the particles and radiation that fill the universe today, basically, the hot Big Bang stuff we're familiar with.
And inflation solves problems, doesn't it? I remember reading about the flatness problem. What was that about?
Right, the flatness problem. It's about the geometry of the universe. Observations suggest the universe is incredibly close to being geometrically flat, meaning parallel lines stay parallel, like on a tabletop, not curved, like on a sphere or a saddle.
Okay, so why is that a problem?
Because for the universe to end up so flat today, its initial density right after the Big Bang had to be unbelievably fine-tuned, like balanced on a knife edge. If it was slightly denser, it would have collapsed back on itself long ago, slightly less dense, and it would have expanded too fast for galaxies to form. The required precision was, well, astronomical.
And inflation fixes that.
It does, beautifully. Think about blowing up a balloon. Even if the balloon's surface starts out wrinkly and curved as you inflate it massively, any small patch looks increasingly flat, right?
Yeah, okay, I see that.
Inflation does the same thing to the universe. That period of hyperexpansion stretches out any initial curvature, smoothing the universe out and making it appear flat, just like we observe, without needing that incredible initial fine-tuning.
So the early vacuum energy was incredibly powerful. What about today? Is there any of that energy left?
Well, that's a huge question in cosmology right now. It's possible that there's a small residual vacuum energy left over from that early phase, or perhaps arising from the current quantum fields.
And if there is some left, what would it be doing?
It could be subtly influencing the universe's expansion even now. This actually connects to another puzzle we had for a while, the age of the universe.
How so?
Early on, when astronomers measured how fast galaxies were moving away from us and extrapolated back, the age they calculated for the universe seemed, well, younger than the estimated ages of some of the oldest stars we could see within it.
Uh-oh. That doesn't sound right. Stars can't be older than the universe they live in.
Exactly. It was a paradox. How could a lingering vacuum energy help with that?
Okay, I'm listening.
If there's a small, persistent vacuum energy today, it would still have that slight negative pressure, creating a gentle, ongoing push or acceleration to the universe's expansion.
So galaxies aren't just coasting, they're speeding up.
Very slightly, yes. But if they're accelerating away faster than we initially thought, it means that when we look back in time, the universe reached its current size more recently than we would have calculated without that acceleration. It makes the universe appear younger in those simple calculations than it truly is.
Ah, okay. So the vacuum energy could stretch out the timeline, resolving the age conflict. That's neat. What about the missing mass problem? Or missing energy, I guess.
Right, another big one. When we measure the curvature of the universe, it looks flat. According to general relativity, a flat universe requires a certain total amount of mass and energy, the critical density. But when we add up all the normal matter we see, plus the dark matter we infer, we still come up short.
There's not enough stuff.
Not enough to make the universe flat. But remember EC and SWOT again. Energy is equivalent to mass density. So if there's a residual vacuum energy spread throughout space,
It could contribute to that total density needed for flatness.
precisely. Some estimates suggested this dark energy, potentially vacuum energy, might make up a huge chunk, maybe 70% of the total mass energy budget of the universe. It could be the missing piece.
Okay, that sounds like a really elegant solution to multiple problems, but is there, like, direct proof? Can we actually see this vacuum energy doing its thing today?
That's where it gets tricky, and the evidence is debated. One way to probe the expansion history is using gravitational lensing.
Lensing, that's when gravity bends light, right? Like a massive galaxy acting as a lens for something behind it.
Exactly. A foreground galaxy, or cluster, can bend the light from a distant object, like a quasar, creating multiple images or distorting its shape. Now, how often we expect to see these lensing events depends on the geometry of space and how much volume there is at different distances.
And how does vacuum energy affect that?
If there's a significant amount of vacuum energy causing accelerated expansion, it changes the relationship between distance and volume over cosmic time. Specifically, it should increase the probability of light rays from distant sources passing close enough to intervening galaxies to be lensed. So, you'd expect to see more gravitational lenses in a universe dominated by vacuum energy. Okay, makes sense. So, do we see more lenses? Well, according to studies like those led by Chris Koschenek mentioned in our sources, the number of gravitational lenses observed seems to be Well, somewhat lower than what you'd predict if vacuum energy makes up that dominant 70% fraction.
Lower. So that argues against a huge amount of vacuum energy.
It suggests that maybe the vacuum energy component isn't quite as large as some models propose. His calculations indicated a lower value might fit the lensing data better.
Huh. So we have a bit of a conflict. Inflation and the age flatness problems seem to point towards vacuum energy, but the lensing data maybe pushes back a bit.
That's a good summary of the tension. Now, there are counter-arguments. Of course, people suggested maybe dust in the lensing galaxies obscures some background quasars, making us miss some lenses.
Right.
But apparently, Kochenik's analysis tried to account for that dust effect and still found a discrepancy. So it's fair to say the exact amount and role of vacuum energy in the current universe is still an active area of research and debate. There isn't full consensus yet.
Okay, fascinating stuff. Let's shift gears a bit. From the cosmic scale down to something we feel every day. Inertia. You know, that resistance when you try to push something heavy or when a car brakes suddenly.
Inertia, yes. So fundamental, yet so mysterious. Even Einstein, Feynman, some of the greatest minds, wrestled with what causes inertia at its deepest level. Why do things resist changes in motion?
Einstein thought maybe it was about connection to distant stars.
He did ponder that. Yeah, Mach's principle, the idea that inertia arises from an object's interaction with all the other mass in the universe. But more recently, a really radical idea has emerged, connecting inertia back to, you guessed it, the vacuum.
The vacuum causes inertia. How on earth would that work? That sounds incredibly counterintuitive.
It does. The idea stems from something called the Davies-Unruh effect. It's a prediction from quantum field theory that says if you accelerate through the vacuum, you won't perceive it as empty.
You won't. What do you perceive?
You'd perceive it as being filled with a warm bath of particles and radiation. The temperature of this bath is proportional to your acceleration. It's bizarre, but it's a solid theoretical prediction.
Okay. A warm bath when you accelerate through nothing. Weird. How does that lead to inertia?
Well, building on that, physicists like Bernhard Heisch and Hal Puthoff proposed a theory. They suggested that maybe inertia itself is an electromagnetic interaction with the vacuum's quantum fluctuations, the so-called zero-point field.
So, interacting with that quantum foam we talked about?
Kind of. Their idea is that the vacuum is filled with a sea of background electromagnetic fluctuations. When a charged particle within an object accelerates, it interacts with this field. Think of it like trying to swim through thick syrup. You feel a drag force resisting your motion.
So accelerating through the vacuum creates a kind of electromagnetic drag force that feels like inertia.
That's the core idea, yes. This resistance to acceleration, generated by interaction with the vacuum field, is inertia, according to their theory.
That's a completely different way of looking at it. But what about the problems? Didn't you say calculating the vacuum energy gives crazy infinite results?
Ah, yes. The elephant in the room. That is a major, major hurdle. When theorists try to sum up the energy of all those vacuum fluctuations, they run into infinities. Even if you cut off the calculation at some physically plausible high energy, the resulting vacuum energy density is vastly larger than what cosmological observations allow.
How much larger?
Like catastrophically larger. Nobel laureate Steven Weinberg famously highlighted this discrepancy. It's off by about 120 orders of magnitude. That's a 1 followed by 120 zeros. It's arguably the worst prediction in the history of physics.
Wow, okay. That's a bit of a problem for a theory relying on that vacuum energy field.
It is. It makes it very difficult to build precise theories based on specific properties of the vacuum energy when we can't even calculate its baseline value correctly. It's a fundamental mystery.
I see. There's also another idea from Andrei Sakharov, something about the vacuum not having gravitational effects.
Right. Sakharov proposed an alternative where gravity itself might be an emergent phenomenon related to vacuum fluctuations, but in a way that cleverly avoids having the vacuum energy itself gravitate. It's an interesting idea, trying to sidestep the huge energy problem, but it also faces its own theoretical challenges and hasn't become the mainstream view.
Still, this vacuum inertia connection, even with the problems, it's really thought-provoking. It makes you wonder, could you, manipulate the vacuum to reduce inertia? That sounds like straight-up science fiction warp drives, antigravity.
Oh, absolutely. It heads straight into speculative territory. The researchers involved, like Heisch and Puthoff, acknowledge that. If inertia is a vacuum effect, then modifying the vacuum state around an object could, in principle, modify its inertia.
So switch off inertia and zoom away.
Well, that's the ultimate sci-fi dream, isn't it? But they're quick to point out that many things once thought impossible, like flight or nuclear energy, eventually became real. Hayes has suggested maybe more realistic goals, like perhaps subtly altering inertia at the atomic level, rather than making entire spacecraft inertialess overnight. Still highly speculative, of course.
Still cool to think about. And there was also a mention of the vacuum maybe helping form galaxies.
Yes, another potential cosmic role. Some research suggests that quantum fluctuations in the very early universe could have actually accelerated charged particles. These accelerated particles might have then acted as seeds, helping gravity pull matter together to form the first stars, galaxies, and the large-scale structures, the cosmic web that we see today.
So the nothing of the vacuum might have helped build the something of galaxies.
Potentially, yes. It's another way the vacuum's activity could be fundamental to the universe's structure. Again, research is ongoing.
Okay, so the vacuum might be behind cosmic expansion, inertia, maybe even galaxy formation. But can we actually do anything practical with it? What about the Casimir effect?
Ah, the Casimir effect. This is really cool because it's not just theory. It's been experimentally measured. It's tangible proof that vacuum energy is real.
So what is it exactly?
Imagine you take two perfectly flat, perfectly conducting metal plates and bring them incredibly close together, like nanometers apart in a vacuum.
Okay, tiny gap.
What the Dutch physicist Hendrik Casimir predicted back in the 1940s is that a small attractive force would arise between these plates, pushing them together, and experiments have confirmed it.
A force from nothing, or from the vacuum.
From the vacuum.
Yeah.
The explanation goes back to those virtual particles, specifically virtual photons. Outside the plates, virtual photons of all possible wavelengths can pop in and out of existence. But between the plates, the tiny gap restricts which wavelengths can fit. It sort of excludes the longer wavelength fluctuations.
Like an echo chamber only allowing certain notes.
Exactly like that. So you have fewer vacuum fluctuations allowed between the plates compared to the outside. This creates an imbalance, more pressure from the vacuum fluctuations pushing on the plates from the outside than from the inside.
And that pushes them together. Wow, direct physical evidence of vacuum pressure.
Precisely. It's a very subtle effect, though. The force is incredibly weak unless the plates are extremely close.
How weak are we talking?
Tiny. At separations of, say, 100 nanometers, the pressure is minuscule compared to atmospheric pressure. But it's measurable with sensitive instruments, and it matches the theoretical predictions remarkably well. It proves the vacuum isn't inert.
So if there's a force, there's energy involved. Can we harness it? Could you build a vacuum engine?
People have certainly thought about it. Theorists like Cole and Puthoff explore this. The basic idea is simple. Let the Casimir force push the plates together. As they move, they gain kinetic energy. If they collide, maybe you could capture that energy as heat, then pull them apart and repeat.
A little vacuum-powered piston.
Sort of, yeah. A hypothetical Casimir engine. You'd need to figure out how to reset it, of course. But the principle is about extracting energy from that vacuum pressure difference.
But I'm guessing there's a catch. Is the energy output any good?
Ah, there's the rub. The calculations show the energy you'd get, even from reasonably sized plates collapsing, is absolutely tiny. We're talking fractions of a joule.
So not exactly powering a city.
Not even close. To get any useful amount of power, you'd need microscopic plate systems, maybe nanomachines, operating at incredibly high speeds, billions or trillions of cycles per second. The technological challenges are just immense, far beyond anything we can currently build.
Okay, so fascinating proof of concept, the Casimir effect, but tapping it for energy is, well, a very long shot for now.
That sums it up well. It's fundamentally interesting, tells us the vacuum is energetic, but as a practical power source. Extremely difficult, maybe impossible on a large scale.
Right. So let's try and pull all these threads together. This nothing, the vacuum, turns out to be potentially, well, almost everything. It might drive cosmic expansion, maybe explain inertia. It demonstrably exerts force through the Casimir effect and holds this vast, albeit maybe inaccessible, energy.
It's truly undergone a revolution in our understanding, hasn't it? From just empty space to perhaps the most fundamental and active stage on which reality plays out. Its potential roles are staggering: cosmology, particle physics, fundamental forces.
But as we've discussed, there are still huge questions. The energy calculation disaster, the debates about dark energy, the speculative nature of inertia manipulation.
Absolutely. It's a field ripe with mystery and ongoing investigation. We have strong evidence the vacuum is active, but nailing down its precise properties and its exact influence on everything from the Big Bang to everyday forces. That's still very much frontier science.
It really makes you think differently about the very fabric of reality, doesn't it? What else is hiding in that nothingness that we haven't even thought to look for yet?
That's the exciting part. Exploring the vacuum could unlock deeper secrets about the fundamental laws of nature, maybe leading to physics we can't even conceive of right now. It's a deep well of potential discovery.
The vacuum. Far from being empty nothingness, it seems to be a fundamental and incredibly active ingredient in the universe. From the largest cosmic scales to the smallest subatomic particles, its influence may be profound. What might the future hold as we continue to probe the secrets of this nothing? Could we one day truly harness its power or even manipulate the very inertia of matter? This exploration of the vacuum certainly gives us much to consider about the nature of reality itself. Until next episode.